So here's something worth thinking about as you settle in tonight. Right now, somewhere in the world, a crane is swinging a steel beam through the air. It's probably happening in Shanghai or Dubai or New York or London. The beam weighs about 15 tons. It's dangling from a cable 1,000 feet above the street, and a team of ironworkers is waiting to catch it. They'll bolt it into place, and that beam will become part of a skeleton. A skeleton designed to hold thousands of people, to resist hurricane-force winds, to sway without breaking, to carry a weight so enormous that if you tried to imagine it all at once, every desk, every filing cabinet, every human body, every concrete slab, every pipe full of water, every air conditioning unit, your mind would simply give up. It would round it off to a very large number, and then it would move on, because that's what we do. We trust these buildings. We walk into them without thinking. We press the elevator button and ride up 40 floors and sit down next to a window. And never once does our brain send us a signal that says, hey, we're floating 400 feet above the ground, held up by nothing but the cleverness of strangers. We just trust it, the way we trust the ground. But the ground has been there for 4.5 billion years. That building has been there since maybe 2004. Someone designed it. Someone did the math. Someone poured the concrete and welded the joints and tested the soil and decided that this particular patch of earth could hold this particular impossible thing. And here's what's really remarkable. If you look closely at how that building stays standing, you find yourself tracing a line backward through time, a line that starts in the present, with gleaming glass and steel, and computers that model wind loads down to the pound, and runs all the way back to a moment in the late 19th century when a handful of architects and engineers in Chicago and New York were trying to figure out something that had never been done before. They were trying to build higher than anyone had ever built. And they didn't have computers. They didn't have modern steel. They didn't have safety nets or hard hats or air conditioning. They had bricks. They had iron. They had steam-powered cranes and a willingness to take risks that would seem insane today. But here's the problem they were up against. For most of human history, if you wanted to build a tall building, you had exactly one option. You made the walls thick. Very, very thick. You stacked stone or brick or concrete, and the weight of the upper floors pressed down on the lower floors. And the walls at the bottom had to be thick enough to carry all that weight without crushing. This is called a load-bearing wall system. It's the oldest construction method in the world, and it has a fundamental, inescapable limit. The taller you go, the thicker the walls at the bottom have to be. At some point, the walls become so thick that there's almost no usable space left inside. You end up with a solid block of material with tiny little rooms carved into it. Not exactly practical. The Monadnock building in Chicago, completed in 1891, is the most extreme example of this. It's 17 stories tall. That doesn't sound like much by today's standards, but in 1891, it was astonishing. And the walls at its base are 6 feet thick. 6 feet of solid brick, just to hold up 17 stories. That was essentially the limit. You couldn't go much higher with load-bearing masonry. The physics simply wouldn't allow it. So for centuries, the height of buildings was capped by the strength of their walls. And then, in the second half of the 1800s, 2 inventions changed everything. The first was structural steel. The second was the elevator. Let's start with steel, because it's the one that matters most for the structure. Steel is iron with a small amount of carbon mixed in, usually less than 2%. And that tiny bit of carbon transforms the material. Iron alone is brittle. It's strong in compression, meaning it handles being squeezed just fine. But it's weak in tension. Pull on it, bend it, and it can snap without warning. Steel, on the other hand, is strong in both compression and tension. You can push on it, pull on it, bend it, and it responds predictably. It deforms before it breaks, which means it gives you warning. Engineers call this ductility, and it's one of the most important properties a structural material can have. A ductile material doesn't suddenly fail. It stretches, it bends, it tells you it's in trouble before it lets go. Brittle materials, cast iron, glass, unreinforced concrete, they just snap. No warning. Ductility is what lets engineers sleep at night. In 1856, an Englishman named Henry Bessemer developed a process that made steel cheap and abundant. He figured out how to blow air through molten iron to burn off excess carbon, producing steel quickly and in large quantities. Suddenly, you could make steel beams and columns at a price that made them practical for construction. And once you had affordable structural steel, the entire logic of building design changed. Here's why. With masonry, the walls are the structure, but with steel, you can build a frame, a skeleton of columns and beams, and then you can hang the walls on that frame. The walls become just a skin, a barrier against wind and rain. They don't carry any load at all. This is the fundamental idea behind every skyscraper ever built. And it was revolutionary. It meant the walls could be thin. They could be made of anything: brick, terracotta, stone, glass. And because the walls didn't have to get thicker as the building got taller, there was no theoretical limit to height anymore. The structure was the frame, not the walls. The person usually credited with building the first true skyscraper is William LeBaron Jenney, an engineer and architect working in Chicago. In 1884, he designed the Home Insurance Building, a 10-story office building that used a steel and iron frame to carry the weight of the floors and the exterior walls. It wasn't a pure steel frame. It used cast iron columns and wrought iron beams and steel beams in some places. But the key innovation was there. The frame carried the load. The masonry walls were supported by the frame, not the other way around. They were, in a sense, just along for the ride. 10 stories doesn't sound like a skyscraper to us. But in 1884, it was a different world. And more importantly, it wasn't the height that mattered, it was the method. Jenney proved that a metal frame could support a tall building, and that opened the door to everything that came after. Now, Chicago is not a coincidence here. The reason so much of early skyscraper history happened in Chicago has to do with a disaster. In 1871, the Great Chicago Fire burned through the city's core, destroying about 17,000 structures. The rebuilding effort that followed was enormous, and it attracted architects and engineers from all over the country, all of them eager to try new ideas. Chicago became a laboratory for building innovation in a way that no other city was at that time. But there was another obstacle to building tall, and it wasn't structural. It was human. Who wants to walk up 20 flights of stairs? 5 stories was already pushing it for most people. Without a safe, reliable way to move people vertically, there was no point in building higher because no one would rent the upper floors. Elisha Otis is the name most people know here, and his contribution wasn't actually inventing the elevator. Hoisting platforms had existed for centuries. What Otis did in 1854 was demonstrate a safety mechanism. He stood on a platform at the Crystal Palace exhibition in New York, had the lifting rope cut, and the platform didn't fall. His safety catch, a spring-loaded mechanism that grabbed onto the guide rails if the rope broke, meant that passenger elevators were now safe enough for regular use. It was pure showmanship. He had a guy with an axe cut the rope while he stood up there in front of a crowd. But it worked. People saw it and thought, okay, maybe I'd ride in one of those. By the 1870s and 1880s, hydraulic and then electric elevators were being installed in buildings across American cities. And suddenly, the upper floors of a building weren't a punishment, they were a premium. Higher floors meant better views, less street noise, more light. The economics of tall buildings flipped completely. The top floors went from being the least desirable to the most desirable, and that meant there was real money to be made by building higher. So, you've got steel frames and you've got elevators, and together they create the conditions for the skyscraper. But having the conditions isn't the same as having the thing itself. There were still enormous problems to solve. How to dig foundations deep enough, how to brace the frame against wind, how to get water and heat and eventually electricity to every floor, how to fireproof the steel so it wouldn't soften and buckle in a blaze. Each of those problems has its own story, its own cast of characters, its own sequence of failures and breakthroughs. And one of the most remarkable things about this whole story is how much of it happened through sheer trial and error. These early engineers were working at the very edge of what was known. They didn't have building codes. They didn't have wind tunnel data. They didn't have computers. They had intuition, experience, and a willingness to try things that had never been tried before. Sometimes it worked, sometimes it didn't. But every failure taught them something, and every success built on the last. By the early 1900s, the skyscraper had become a symbol of American ambition and ingenuity. The race to build the tallest building in the world was on, and it was fueled by ego, by profit, and by a deep-seated belief that nothing was impossible. The Chrysler Building, the Empire State Building, the Woolworth Building. These weren't just office buildings. They were monuments. They were statements. They were proof that human beings could reach higher than anyone had ever imagined. But here's the thing. The race for height wasn't just about building taller. It was about building smarter. Each new record-breaking building pushed the boundaries of engineering. It forced engineers to solve problems they hadn't even known existed. And those solutions, the steel frame, the wind brace, the curtain wall, the deep foundation, those solutions didn't just make taller buildings possible. They made all buildings better, safer, more efficient, more comfortable. The skyscraper is one of the great achievements of human civilization. It's a testament to our ability to work together across generations, to build on the work of those who came before us, to imagine something that doesn't exist, and then bring it into being through sheer force of will. Every time you walk into a tall building, you're walking into a piece of that history. You're standing on the shoulders of people who risked their lives and their reputations to prove that the impossible was possible. And tonight, as you lie here, surrounded by the quiet hum of civilization, think about what it took to build that building around you. Not just the steel and concrete, but the ideas, the people, the 150 years of trial and error that led to this moment, the architects and engineers who looked at a problem that had defeated everyone before them and said, "We can solve this." The workers who climbed steel beams hundreds of feet in the air with nothing but their hands and their courage. The visionaries who refused to accept that there was a limit to how high we could go. That's what we're going to explore. How skyscrapers actually get built, from the dirt up. How the physics and the engineering come together to create these impossible structures. How the people who designed and built them solved problems that seemed unsolvable. And why, after all these years, the skyscraper still stands as one of the greatest achievements of human ingenuity. Now let's go back to the beginning. Let's go back to the ground beneath your feet. Because every skyscraper starts not with the building itself, but with what's underneath it. Let's go back, way back, before steel, before elevators, before anyone even dreamed of a building that could scrape the clouds. Let's go back to a time when the only way to build tall was to build thick. Imagine you're an architect in ancient Rome. You want to build a multi-story apartment building, a insula, where dozens of families can live. How do you do it? You stack stones and bricks. You make the walls at the bottom thicker than the walls at the top, because the bottom walls have to carry everything above them. The taller you go, the thicker the walls have to be. And there's a limit. A hard physical limit where the walls become so thick that the space inside is barely worth having. This is the tyranny of mass. The building's own weight is its worst enemy. The higher you reach, the more material you need just to hold the thing up. And that material has weight of its own, so you need even more material to hold that up. And on, until you hit a wall, a literal wall, where going any higher is simply impossible. For thousands of years, this was the fundamental problem of architecture. Cathedrals, palaces, fortresses, all of them were limited by the compressive strength of stone and the thickness of their walls. The Gothic cathedrals of Europe, with their soaring spires and flying buttresses, were incredible achievements. They pushed the limits of masonry construction about as far as they could go. But even the tallest cathedral spire, the one at Strasbourg, only reached about 460 feet. And that's with a spire, a lightweight, tapering structure that doesn't have to carry heavy floors and thousands of people. The practical limit for a load-bearing masonry building with multiple floors was far lower, somewhere around 10 to 15 stories. Beyond that, the walls at the base became so thick that they consumed most of the floor area. You could build a 20-story stone building, but the first floor would be mostly wall, with only a small room in the center. Not exactly a useful space. And here's what's really important to understand about this problem. It's not just about the strength of the material. It's about the geometry of the structure. When you double the height of a building, you roughly double the weight that the lower walls have to support. But the walls themselves also get heavier as they get thicker. The relationship between height and required wall thickness is not linear. It's exponential. Every additional story costs more in wall thickness than the one before it. The Monadnock building in Chicago, completed in 1891, is the ultimate expression of this. It's 17 stories tall, and its walls at the base are 6 feet thick. 6 feet of solid brick. That's not a wall anymore. That's a fortress. The Monadnock is a beautiful building, but it was also a dead end. It represented the absolute limit of what was possible with load-bearing masonry. To go higher, you would need walls that were 8 feet thick, then 10 feet thick, and soon you'd have no usable space at all. So where did that leave architects and builders? For centuries, they had no other options. They could improve the quality of their stone, they could use better mortar, they could employ flying buttresses to reduce the load on the walls, but the fundamental limitation remained. The walls had to carry the load, and that meant they had to be thick. And then, in the 19th century, everything changed. It started with iron. Cast iron columns had been used in buildings since the late 1700s. They were a genuine improvement over masonry. A slender iron column could carry the same load as a massive brick pier, and it took up far less space. Cast iron was strong in compression, and it could be cast into complex shapes. Builders began using it for columns in factories, mills, and market halls. But cast iron had a problem. It was brittle. It was strong when you pushed on it, but weak when you pulled on it or bent it. A cast iron column could snap without warning if it was subjected to a sideways force, like wind. It wasn't safe for tall buildings, where wind loads are a real concern. The next step was wrought iron. Wrought iron was tougher and more ductile than cast iron. It could bend before breaking. Builders began using wrought iron beams in floor structures, but it was still relatively expensive, and it wasn't strong enough for the demands of a truly tall building. What was needed was something stronger, something more consistent, something that could be produced in large quantities at a reasonable cost. What was needed was steel. But steel had been around for centuries. Ancient civilizations produced small amounts of steel, but it was rare and expensive. The problem was the process. Making steel required heating iron ore with carbon and then carefully controlling the amount of carbon that remained in the finished product. Too much carbon made the steel brittle. Too little made it weak. The process was slow, laborious, and inconsistent. Then, in 1856, Henry Bessemer introduced a process that changed everything. He figured out how to blow air through molten iron to burn off impurities and control the carbon content. The air oxidized the carbon and other impurities, turning them into gases that escaped from the iron. The result was steel of consistent quality, produced quickly and cheaply. The Bessemer process revolutionized the steel industry. Suddenly, steel was available in large quantities at a price that made it practical for construction. But having steel was only half the battle. The other half was figuring out how to use it effectively. For centuries, architects had been trained to think of buildings as boxes of masonry. The walls were the structure. The walls held everything up. It took a radical rethinking of the entire process of building to see the wall not as a structural element, but as a skin. The person who made that leap was William LeBaron Jenney. Jenney was an engineer and architect who had worked on some of the largest projects of his day. He understood the limitations of masonry, and he understood the potential of iron and steel. In 1884, he designed the Home Insurance Building in Chicago. It was only 10 stories tall, but it was revolutionary. Jenney's building used a frame of cast iron columns and wrought iron beams to support the floors and the exterior walls. The walls themselves were just hung on the frame. They didn't carry any load at all. This was the first true skeleton structure. The frame was the structure. The walls were just there to keep out the weather and to look nice. It sounds obvious now, but in 1884, it was a revelation. Jenney had demonstrated that the walls were not necessary for the building's structural integrity. The frame was. This meant that the walls could be as thin as you wanted. They could be made of lightweight materials that didn't have to support anything. And because the walls didn't get thicker as the building got taller, there was no longer a theoretical limit to height. The Home Insurance Building was a modest building by today's standards, but it was the spark that ignited the skyscraper revolution. Soon, architects and engineers across the United States were experimenting with iron and steel frames, trying to push the limits of what was possible. The race to build the tallest building in the world was on, and it was driven not just by engineering, but by economics. In cities like Chicago and New York, land was scarce and expensive. The only way to create more space was to build up. A building that could hold more tenants on a small plot of land was a building that could generate more revenue. The skyscraper was not just a feat of engineering, it was a machine for making money. Architect Louis Sullivan, one of the greats of the Chicago school, understood this better than anyone. Sullivan believed that the skyscraper should be expressive of its height. It shouldn't try to hide how tall it is, it should celebrate it. Sullivan designed buildings with 3 distinct parts: a base, a tall shaft, and a top. He wanted the building to look vertical, to emphasize its verticality, and he used the new steel frame to achieve that effect. His auditorium building in Chicago, completed in 1889, was a demonstration of these principles. It was 22 stories tall, and it had a steel frame that allowed the walls to be relatively thin. The building was a landmark, and it solidified Chicago's reputation as the birthplace of the skyscraper. But even with steel, there were still challenges. The steel frame, as revolutionary as it was, had a weakness: fire. In a fire, steel loses its strength. At temperatures above 1,000 degrees Fahrenheit, steel begins to soften. At 1,500 degrees, it loses about half its strength. A fire could cause steel beams to sag, columns to buckle, and the entire frame to collapse. The Great Chicago Fire of 1871 had already shown how devastating fire could be. The early skyscraper builders knew that they had to protect the steel from fire. Their solution was fireproofing. They wrapped the steel beams and columns in materials that insulate them from heat. In the earliest skyscrapers, this meant encasing every steel member in terracotta tiles. The tiles were heavy, they were expensive, and they took time to install. But they were absolutely essential. If you've ever seen an old building being demolished and noticed that the steel beams are wrapped in what looks like clay blocks, that's terracotta fireproofing. The critical importance of fireproofing was demonstrated again and again throughout the 20th century, sometimes in the most tragic ways. But the early engineers got this one right, mostly because they'd already lived through the consequences of getting it wrong. Chicago's building codes after the Great Fire were among the strictest in the world, and they mandated substantial fire protection for structural steel. New York followed with its own codes, and these requirements shaped the way skyscrapers were built. Every piece of structural steel had to be protected, which meant that the fireproofing was designed right into the construction sequence. You'd erect the steel, then the fireproofing crews would follow behind, floor by floor, wrapping everything before the interior finishes went in. So, by the end of the 19th century, the essential elements of the skyscraper were in place: structural steel, fireproofing, and the elevator. But the race was only just beginning. The early skyscrapers of Chicago and New York were impressive, but they were still relatively short by today's standards. The Woolworth Building, completed in 1913, was 55 stories tall and was the tallest building in the world for 16 years. The Empire State Building, completed in 1931, was 102 stories tall and held the record for more than 40 years. Each of these buildings pushed the boundaries of what was possible. Each one required new materials, new techniques, and new ways of thinking about how a building works. And each one, in its own way, was a response to the fundamental problem of the skyscraper. How do you build something that tall and keep it standing? The answer, as it turned out, was to think of the building not as a single structure, but as a system of interconnected systems. The frame is the skeleton. The walls are the skin. The elevators are the circulatory system. The mechanical systems are the lungs. And the foundation is the root system that anchors the whole thing to the earth. And just like a living organism, a skyscraper has to be able to adapt to its environment. It has to be able to withstand the forces of nature, wind, rain, earthquakes. It has to be able to move and flex without breaking. It has to be able to carry its own weight and the weight of everything inside it. This is the challenge that architects and engineers have been wrestling with for more than a century. But here's the thing about that challenge. Every time it seems like we've reached the limit, every time someone says, "You can't build any taller," some engineer somewhere finds a way. They find a new material, a new system, a new way of thinking about the problem, and the height record gets broken again. So the next time you walk into a tall building, remember this: you're not just walking into a building, you're walking into a piece of history, a history that stretches back more than 100 years, a history of invention, of struggle, of human ingenuity, a history of people who refused to believe that there was a limit to how high we could go. And that history is far from over. The buildings of the future will be even taller, even more sophisticated, even more astonishing. But they will all build on the work of those who came before. Let's go deeper. Let's go underground. Because every skyscraper, no matter how tall, starts with a hole in the ground. The Empire State Building rises 1,250 feet above the streets of Midtown Manhattan. It stands on a plot of land that was once the site of the old Waldorf Astoria Hotel. When they started digging for the foundation in 1930, they went down 70 feet. 70 feet straight down through soil and rock and groundwater. That's deeper than the building is tall, if you measure from the sidewalk to the first floor. The foundation of the Empire State Building is a hole in the ground almost as deep as a 7-story building. But here's the thing. That hole wasn't just a hole. It was a carefully engineered excavation designed to reach a layer of solid rock called Manhattan schist. And what's Manhattan schist? It's the bedrock that holds up the entire island of Manhattan. It's old, it's hard, and it's strong. It can support almost any weight you put on it. But it's not the same everywhere. In lower Manhattan, the schist is close to the surface, sometimes only 30 or 40 feet down. That's why the earliest skyscrapers clustered downtown, around Wall Street and the financial district. The bedrock was close, and building foundations were relatively cheap. But in Midtown, the schist slopes away, plunging down 100 feet or more. The Empire State Building sits on a piece of bedrock that is almost 200 feet below the surface. That's a long way to dig. And what's between the surface and the rock? Soil, clay, sand, gravel, and water. Lots of water. The water table in Manhattan is not that far below the street. If you dig deep enough, you will hit groundwater. And groundwater is a problem. It flows, it seeps. It can turn a dry excavation into a muddy lake in a matter of hours. So how did the builders of the Empire State Building deal with this? They used something called a caisson. A caisson is a giant underground box, open at the bottom and sealed at the top. You lower it into the ground, and then you dig out the soil from underneath it, and the caisson sinks under its own weight. As it sinks, you add more sections on top, building a tube that goes all the way down to bedrock. Then you fill the whole thing with concrete, creating a solid pier that goes from the rock to the surface. The building sits on these piers. It's like building a foundation on stilts, but the stilts are underground. Now, here's where the story gets dangerous. In the early days of skyscraper construction, caissons were excavated by hand. Men would climb down into these dark, cramped chambers and dig out the soil with shovels. They'd work in water, in mud, in air that was thick with dust and fumes. Sometimes the air would get so bad that they'd pass out. And sometimes, if the caisson was particularly deep, they'd use compressed air to keep the groundwater out. Compressed air is a clever solution to a difficult problem. If you pump enough air into the caisson, the air pressure pushes back against the groundwater and keeps it out. The chamber stays dry. But there's a downside. The men working in that compressed air environment have to be carefully monitored. They have to spend time in an airlock to acclimate to the pressure before they go in, and they have to spend time in an airlock when they come out. And if they come out too quickly, they get sick. Very sick. The illness is called caisson disease, or decompression sickness, or the bends. It happens when the nitrogen in your blood comes out of solution and forms bubbles in your tissues. Those bubbles can cause joint pain, paralysis, and death. During the construction of the Brooklyn Bridge in the 1870s, caisson disease killed several workers and left the chief engineer, Washington Roebling, paralyzed for life. Roebling actually had to direct the rest of the bridge's construction from an apartment window, using a telescope and a system of hand signals with his wife. By the time the Empire State Building was being built, in 1930, caisson disease was a known hazard and there were safety protocols in place, but it was still dangerous work. Men would work in the compressed air for only 2 or 3 hours at a time. They would be paid extra for the risk, and they still got sick. Some of them died. The foundation of a skyscraper is the part of the building that you never see, but it's the part that makes everything else possible. It is the root system that anchors the entire structure to the earth. Without it, the building would sink, tilt, or collapse. And here's the thing. The challenges of foundation construction aren't the same everywhere. Different cities, different soils, different problems. In Chicago, the problem is clay. Soft, wet, compressible clay that goes down for hundreds of feet. If you build a heavy building on Chicago clay, it will sink, and it won't sink evenly. One side might sink more than the other. That's called differential settlement. And it can crack walls, break pipes, and make the building uninhabitable. The early Chicago skyscrapers solved this problem by using massive concrete foundations that spread the weight over a large area. like wide snowshoes. They called these raft foundations. They would dig a big pit and pour a thick concrete slab across the entire footprint of the building. The building's weight would be distributed across the slab, and the slab would distribute the weight across the clay. It would still sink a little bit, but the sinking would be uniform. The building wouldn't tilt. In places with very soft soil, like parts of Florida or the Gulf Coast, they use something called deep foundations. Instead of spreading the weight over a large area, they transfer it down to a deeper, stronger layer of soil or rock using piles. Piles are long, slender columns made of steel, concrete, or wood. They are driven down into the ground using a huge hammer until they hit a layer that can support the weight. In some cases, piles are driven down as far as 200 feet. Think about that. A building that rises 1,000 feet above the ground might have piles that extend 200 feet below the ground. That's a total length of 1,200 feet, from the bottom of the pile to the top of the building. The structure is as deep as it is tall. And here's what's really interesting. The science of foundations has advanced tremendously since the days of caissons and raft slabs. Today, engineers use sophisticated computer models to simulate how a building's foundation will interact with the soil. They can test different foundation designs on a computer before they ever put a shovel in the ground. They can account for the weight of the building, the type of soil, the water table, and even the effects of nearby buildings. But even with all that technology, the basic principles are the same as they were 100 years ago. You have to get the weight of the building down to something that can support it. If you can't find something solid near the surface, you go deeper. And if you go deep enough, you will find something solid. The Earth is not infinitely compressible. It's not infinitely weak. There is always a layer of rock or dense soil somewhere down there. It's just a question of how far you have to go to reach it. And the farther you have to go, the more it costs. Foundations are one of the most expensive parts of a skyscraper. In some cases, they can account for 25% of the total construction cost. That's a lot of money to spend on something that no one will ever see. But here's the thing. The foundations of a skyscraper are not just about holding the building up. They also have to keep the building from falling over. Wind, earthquakes, and even the weight of the building itself can create forces that try to tip it over. The foundation has to resist those forces. It has to be strong enough to keep the building upright, even in the most extreme conditions. That's why the foundations of modern skyscrapers are so massive. The foundations of the Burj Khalifa in Dubai, the tallest building in the world, consist of a concrete mat that is 12 feet thick, supported by piles that go down more than 160 feet. That's a foundation that weighs thousands of tons, just to support the building above. But the Burj Khalifa is a special case. It's built on sand, which is not ideal for a super tall building. The engineers had to design a foundation that would work in that environment. They used a technique called a friction pile foundation. The piles don't rest on solid rock. They are held in place by the friction of the soil around them. The weight of the building is transferred to the soil through the sides of the piles. It's a delicate balance. If the soil shifts, the building shifts. So the engineers had to be very careful. But they made it work. And that's the thing about skyscraper foundations. They are not one size fits all. Every building is different. Every site is different. The engineering is always tailored to the specific conditions. So the next time you walk into a tall building, think about what's beneath you. Think about the 70 feet of soil, the caissons, the compressed air, the sweat, and the risk. Think about the engineers who figured out how to anchor that building to the earth. And think about the workers who actually did the digging. They are the unsung heroes of the skyscraper. They are the ones who laid the foundation for everything that came after. And now that we've gone down into the dark, it's time to come back up. It's time to start building the steel skeleton that will climb toward the sky. Now we come up from the darkness. The The foundation is in place, the concrete is cured, and it's time to build the part of the skyscraper that everyone actually sees. It's time to erect the steel frame. If you've ever watched a skyscraper being built, you know what this looks like. A tower crane rises above the site, lifting steel beams into the air. Iron workers, wearing hard hats and safety harnesses, walk along the beams, guiding them into position. Bolts are driven into place. Welds are made. Slowly, floor by floor, the building climbs toward the sky. But what you're seeing on the surface is only part of the story. The real story is happening behind the scenes, in the fabrication shops and the engineering offices. Because before a single beam is lifted into place, thousands of hours of work have already been done. Every piece of steel in a modern skyscraper is prefabricated. It's cut to length, drilled with bolt holes, and marked with a unique identification number in a factory miles away from the construction site. When it arrives at the site, it's ready to be installed. There's no cutting or drilling on site. The beams fit together like pieces of a giant three-dimensional puzzle. This is called prefabrication, and it's one of the key innovations that make skyscraper construction possible. It saves time, it reduces errors, and it allows for much faster construction. The Empire State Building, completed in 1931, was built using prefabrication. The steel for that building was fabricated in Pittsburgh, shipped to New York, and installed at a rate of 4.5 floors per week. That's astonishing speed, even by today's standards. But prefabrication is only one part of the puzzle. The other part is the structural system itself, and here the engineers have a choice. There are several different ways to build a steel frame, and each one has its own advantages and disadvantages. The simplest system is the rigid frame. In a rigid frame, the beams and columns are connected with rigid joints that resist bending. The building's lateral stability, its ability to resist wind and earthquake forces, comes from the stiffness of these connections. The connections are heavy and they require a lot of steel, but they allow for open, column-free floor plans. The next step up is the braced frame. In a braced frame, diagonal beams are added to the structure to create triangles. Triangles are the most stable geometric shape. A triangle can't collapse without one of its sides breaking. The diagonals in a braced frame provide tremendous lateral stability. The downside is that the diagonals take up space and can interfere with floor plans. Then there's the tube frame, invented by Fazlur Khan in the 1960s. In a tube frame, the exterior columns are spaced very close together, creating a rigid tube around the perimeter of the building. The building acts like a giant hollow box, resisting wind loads by transferring them down to the foundation. This system is incredibly efficient, and it allows for very tall buildings with relatively little steel. And then there's the bundled tube, which Khan also invented for the Sears Tower in Chicago. In a bundled tube, multiple tubes are bundled together, creating a structure that is even stiffer than a single tube. The Sears Tower is actually 9 tubes bundled together, each one terminating at a different height, which creates the building's distinctive stepped profile. Each of these systems has its own engineering challenges, but the biggest challenge, the one that keeps structural engineers up at night, is the connection. How do you connect the beams and columns together so that they act as a single, unified structure? In the early days of skyscraper construction, they used rivets. Rivets are like permanent bolts. A hot rivet is inserted into a hole in the steel, and then a pneumatic hammer is used to mash the other end, creating a second head that holds the pieces together. As the rivet cools, it contracts, pulling the steel plates tightly together. The thermal contraction creates a clamping force that makes the joint incredibly tight. A single large building might require hundreds of thousands of rivets. The Empire State Building used about 2.5 million of them, and every single one was heated, thrown, caught, placed, and hammered by hand. The riveting gangs developed an almost musical rhythm. The ring of the forge, the arc of the glowing rivet through the air, the staccato hammering of the pneumatic gun. You could hear a skyscraper going up from blocks away. Today, rivets have been almost entirely replaced by high-strength bolts and welding. Bolts are faster to install, and the quality is easier to inspect. Welding creates continuous connections that can be stronger than riveted joints, but the basic principle is the same. The connections have to be strong enough to transfer the forces from one member to another. And those forces are enormous. A single column at the base of a 100-story building might carry a load of 10 million pounds. That's about 5,000 tons. The column has to be strong enough to support that load, and the connections at the top and bottom of the column have to be strong enough to transfer that load to the foundation. And then there's the wind. Wind can create lateral forces of tens of thousands of pounds on a tall building. The building has to be designed to resist those forces without excessive sway. If the building sways too much, the occupants will feel it. They'll get motion sickness. They'll feel unsafe. The goal of the structural engineer is to design a frame that is strong enough to resist the loads, stiff enough to limit the sway, and efficient enough to be economical. It's a balancing act. Too much steel, and the building is too expensive. Too little steel, and the building is unsafe. And then there's the fire protection. We talked about fireproofing earlier, but it's worth emphasizing. Steel loses its strength at high temperatures. In a fire, unprotected steel can soften and collapse. That's why every piece of structural steel in a modern skyscraper is fireproofed. It's either encased in concrete, wrapped in a fire-resistant material, or coated with a special paint that expands when heated and insulates the steel. The fireproofing is installed after the steel is erected. It's a slow, painstaking process, but it's absolutely essential. Without it, the building would be a death trap. So, how do you actually erect the steel? How do you lift those giant beams into the air? The answer is the tower crane. The tower crane is one of the most iconic pieces of construction equipment. It rises above the building, growing taller as the building grows. The crane is supported by the structure itself. As the building rises, the crane climbs up with it. At the beginning of construction, the crane is at ground level. It's assembled on the ground, and then it starts lifting steel. As the building gets taller, the crane uses hydraulic jacks to climb up the building. It's a slow, careful process, but it works. The crane is the heart of the construction site. Without it, nothing else can happen. The ironworkers who assemble the steel are another essential part of the process. These are the people who walk along steel beams 1,000 feet in the air, guiding them into position, bolting them together. They are highly skilled professionals. They are also, by necessity, incredibly brave. In the early days of skyscraper construction, ironworkers worked without safety harnesses. They walked along steel beams 6 inches wide, hundreds of feet in the air, with nothing to catch them if they fell. The casualty rates were staggering. During the construction of the Empire State Building, 5 workers were killed. That was actually considered a good safety record for the time. Today, safety is taken much more seriously. Hard hats are mandatory. Safety harnesses are required. Safety nets are installed below the work area. The casualty rates have dropped dramatically, but the job is still dangerous. The work is still done at extreme heights in all kinds of weather, and the work is still done with incredible precision. The steel beams have to fit together perfectly. The connections have to be aligned. The columns have to be plumb, perfectly vertical. If a column is off by even a fraction of an inch at the base, it can be off by several inches at the top. That's enough to cause serious problems. So the ironworkers use plumb bobs and levels and laser alignment tools to make sure everything is exactly where it should be. It's a painstaking process, but it's essential. But even the best ironworkers can only work with what they're given. The steel itself has to be manufactured to exact specifications. That's where the fabrication shop comes in. In the fabrication shop, the steel beams are cut to length. The bolt holes are drilled, and the pieces are marked with their identification numbers. The fabrication shop is like a giant metalworking factory. It's loud and hot and full of sparks, and it's where the building is born. The fabrication shop is also where the quality control happens. Every piece of steel is inspected to make sure it meets the specifications. If a piece is defective, it's rejected. The fabrication shop is the final line of defense against structural failure. Once the steel is fabricated, it's loaded onto trucks and shipped to the construction site. And then the whole process starts all over again. Crane lifts the steel, ironworkers install it, and the building rises, floor by floor. It's a beautiful system, really. It's a symphony of coordinated effort, all working together to create something that didn't exist before. And at the heart of it all is the steel frame, the skeleton that holds the whole thing up. So the next time you look at a skyscraper, think about that skeleton. Think about the thousands of tons of steel, the millions of bolts and welds, the ironworkers walking along beams 1,000 feet in the air. Think about the engineering that went into making it all work. Because that skeleton is what makes the building possible. Without it, the building would be just a pile of rubble. And the skeleton is the key. That's the big idea. That's what separates the skyscraper from everything that came before. The skeleton is what allows the walls to be thin, the floors to be open, the building to be tall. The skeleton is what makes the skyscraper possible. But the skeleton has to be protected. It has to be wrapped in something. It has to have a skin. And that skin is just as important as the bones inside. The steel skeleton is up. The beams are bolted and welded. The frame stands tall against the sky, a giant grid of metal waiting to be filled in. But if you look at it from the street, you don't see the skeleton at all. You see the skin, the facade, the curtain wall. And here's the thing about the curtain wall. It doesn't hold anything. It doesn't carry any weight. It just hangs there, attached to the frame, keeping the weather out and the people in. It's the thinnest, lightest part of the building, and yet it's the part that defines what the building looks like. The curtain wall is one of the great innovations of skyscraper construction. Before the curtain wall, buildings were heavy. They were made of stone or brick or concrete, and they were thick. The walls were part of the structure. They held the building up. But with the steel frame, the walls no longer had to carry any load. They could be thin. They could be light. They could be made of glass. This was a revolutionary idea. It meant that the building could be transparent. It could be filled with light. It could be a gleaming tower of glass and steel, reflecting the sky and the clouds. It could be a work of art. The first true curtain wall building was the Lever House, completed in New York in 1952. It was a sleek green glass tower that looked unlike anything else on the skyline. It was modern, clean, and almost weightless. It set the standard for corporate architecture for decades to come. But the curtain wall is not just about looks. It has to perform. It has to keep out rain, snow, and wind. It has to insulate against heat and cold. It has to manage condensation. It has to absorb the movement of the building as it sways and expands and contracts. And it has to do all of this for decades with minimal maintenance. So how does it work? Let's start with the simplest element, the glass. Modern skyscraper glass is not the same as the glass in your windows at home. It's specially engineered to meet the demands of a tall building. The most common type of glass used in skyscrapers is called insulated glass. It consists of 2 or more layers of glass separated by a sealed airspace. The airspace is often filled with argon or krypton gas, which are better insulators than plain air. The glass itself may be coated with a special film called a low emissivity coating, which reflects heat back into the building in the winter and reflects solar heat away in the summer. This coating is nearly invisible, but it makes a huge difference in the building's energy efficiency. The glass is held in place by a frame, usually made of aluminum. Aluminum is light, strong, and corrosion-resistant. It's the ideal material for a curtain wall frame. The frame is attached to the building's structure, but it's designed to allow for movement. The building sways in the wind. The steel expands and contracts with temperature changes. The curtain wall has to be able to move with it without cracking or leaking. The seal between the glass and the frame is critical. In older buildings, the seals were made of putty or caulking. Over time, these materials would dry out and crack, allowing water to leak in. Modern buildings use sophisticated seals made of silicone or other synthetic materials that can last for decades. But even the best seals aren't perfect. Water can still find its way through tiny gaps. That's why curtain walls are designed with a built-in drainage system. Water that gets past the outer seal is channeled down through the frame and drained out through weep holes at the bottom of the wall. It's a clever system that acknowledges the reality that no seal is perfect. The curtain wall also has to deal with the building's movement. Tall buildings sway in the wind. The top of the Sears Tower can move more than a foot in a strong wind. The curtain wall has to be able to accommodate this movement. The connections between the glass and the frame are designed to allow for some play. The glass panels are not rigidly fixed in place. They can shift slightly as the building moves. This is called a floating curtain wall, and it's a key innovation in modern skyscraper design. But the curtain wall is not just glass. It can be made of many different materials: stone, metal, terracotta, concrete. Each material has its own advantages and disadvantages. Stone is beautiful and durable, but it's heavy and expensive. Metal is strong and light, but it can corrode. Terracotta is lightweight and can be molded into intricate shapes, but it's fragile. The choice of material depends on the building's design, its budget, and its location. The curtain wall also has to provide some level of fire protection. In a fire, the curtain wall can act as a barrier, preventing the fire from spreading from floor to floor. The frames are designed to resist fire for a certain period of time, giving occupants a chance to evacuate. And then there's the issue of wind. We've talked about wind loads on the structure, but the curtain wall also has to resist wind pressure. On a tall building, the wind pressure on the upper floors can be enormous. The curtain wall has to be strong enough to withstand this pressure without bending or breaking. The curtain wall is also a major factor in the building's energy efficiency. In a typical office building, heating and cooling can account for 50% or more of the energy usage. The curtain wall has a huge impact on these costs. A well-designed curtain wall can reduce energy usage by keeping heat in during the winter and reflecting solar heat away during the summer. This is why modern curtain walls are so sophisticated. They use multiple layers of glass, low emissivity coatings, and argon-filled spaces to achieve very high levels of insulation. Some buildings even use electrochromic glass, which can change its tint in response to sunlight, reducing glare and heat gain. The curtain wall is also a major factor in the building's environmental impact. The production of glass and aluminium is energy-intensive, so a well-designed curtain wall should be designed to last for a long time, reducing the need for replacement. And when it does need to be replaced, the materials should be recyclable. So the curtain wall is not just a pretty face, it's a sophisticated engineering system that has to perform many different functions. It has to be strong, lightweight, weatherproof, fire-resistant, and energy efficient. It has to accommodate movement, and it has to look good. It's a tough assignment, but modern curtain wall systems are up to the task. They are the product of decades of research and development, and they continue to evolve as new materials and technologies become available. And now, the skeleton is wrapped. The building is protected from the elements, but there's still a long way to go before anyone can move in. Because a building without power, water, heat, and cooling is just an empty shell. It's time to think about the mechanical systems. It's time to make the building habitable. The steel skeleton is up. The curtain wall is in place. The building looks finished from the outside, but step inside and you'll find it's still an empty shell. There are no lights, no water, no heat, no air conditioning. The elevators don't work, the toilets don't flush. It's just a hollow box. Making a skyscraper livable is a massive engineering challenge. You're essentially building a vertical city. And just like a city, a skyscraper needs infrastructure. It needs power, water, sewerage, heating, cooling, and communications. It needs to move people up and down. It needs to keep them safe in a fire. It needs to be comfortable, quiet, and clean. All of this is accomplished by the building's mechanical, electrical, and plumbing systems. These are the invisible systems that make the building work. They're hidden behind walls, above ceilings, and below floors. But without them, the building is just a monument. Let's start with the most basic need: water. In a typical skyscraper, water is supplied by the municipal water system. But municipal water pressure is only strong enough to push water up about 6 to 10 stories. Above that, you need pumps. And you can't just have one big pump in the basement. The pressure at the bottom of the pipe would be enormous, enough to blow out fittings and fixtures on the lower floors. The solution is zoned water distribution. The building is divided into vertical zones, each about 20 to 30 stories tall. In each zone, there's a water tank. Water is pumped from the city main up to the first tank, then from that tank up to the next, and so on. It's like a series of locks on a canal. Each pump only has to lift the water a relatively short distance, so the pressure stays manageable. The water in the tanks is gravity-fed down to the floors below. This is why tall buildings always have water tanks on the roof or on intermediate mechanical floors. They're not decorative, they're functional. Now consider the sewage. Water comes in and water has to go out. But here's the problem. Sewage flows downhill. That's fine for the upper floors, but what about the lower floors? The sewage from the upper floors has to pass by the lower floors on its way to the sewer. If you're on the second floor and someone on the 50th floor flushes a toilet, you don't want that waste coming out of your sink. The solution is to break the building into zones for drainage as well. Each zone has its own drainage stack that goes down to a sewer connection at or below grade. This prevents cross-contamination between zones. Then there's the electricity. A skyscraper consumes an enormous amount of power. Lighting, elevators, air conditioning, computers, all of it adds up. The Burj Khalifa, for example, uses as much electricity as a small town. All of that power has to be brought into the building, distributed to every floor, and transformed to the right voltage. Power enters the building at a high voltage and is stepped down through transformers on each floor. The distribution panels route power to different areas of the floor. And of course, there are backup systems. Diesel generators, usually located in the basement or on mechanical floors, can provide power in an emergency. And then there's the heating, ventilation, and air conditioning, often called HVAC. This is the biggest energy consumer in a typical commercial building, often accounting for 40% or more of the building's total energy usage. The HVAC system is the building's lungs. It's responsible for moving heated or cooled air throughout the entire building. In a tall building, you can't just have one central HVAC system. The air pressure at the top of the building is different from the air pressure at the bottom. The temperature on the south side of the building is different from the temperature on the north side. The needs of different tenants are different. The solution is to break the building into zones, just like with water and sewage. Each zone has its own air handling units, which are usually located on mechanical floors, spaced every 20 to 30 stories. The air handling units draw in outside air, filter it, heat or cool it as needed, and then distribute it through ducts to the floors in their zone. The ducts run through the ceiling plenum, the space between the drop ceiling and the floor slab above. This is where you'll find all the hidden infrastructure of the building: ducts, pipes, cables, all carefully routed to avoid conflicts. HVAC systems have gotten much more sophisticated over the years. Modern buildings use variable air volume systems, which can adjust the amount of air being supplied to different parts of the building based on demand. They use heat recovery systems that capture waste heat from the exhaust air and use it to preheat the incoming fresh air. Some buildings even use chilled beams, which are ceiling-mounted fixtures that use chilled water to cool the air, eliminating the need for large ductwork. All of these systems have to be carefully coordinated with the building's structural and architectural design. The ducts and pipes have to fit within the available space. The mechanical floors have to be strong enough to support the heavy equipment. The whole system has to be accessible for maintenance and repair. And then there's one more invisible system that is absolutely essential to the safety of the building: the fire protection system. We've already talked about fireproofing the steel. But fireproofing the steel is only the first line of defense. The building also needs active fire protection systems. That means sprinklers, smoke detectors, fire alarms, and fire suppression systems. Sprinklers are the most important fire protection system in any tall building. They are designed to activate automatically when they detect heat, spraying water on the fire and containing it. In a typical commercial building, sprinklers can contain a fire to the room where it started, giving occupants time to evacuate and firefighters time to respond. Sprinklers are required by building codes in almost all commercial buildings. They are one of the most effective fire safety measures ever invented, but sprinklers alone aren't enough. The building also needs a reliable water supply for the sprinklers. That means a dedicated water main and a fire pump that can provide enough pressure to reach the upper floors. Many tall buildings also have a fire water tank on an upper floor to ensure water is available even if the city water supply fails. The fire alarm system is another critical component. It detects smoke and heat and sounds an alarm to alert the occupants. In a tall building, the fire alarm is usually connected to a central control panel that can pinpoint the location of the fire, allowing firefighters to respond more quickly. And then there are the fire stairs. In a tall building, there are usually at least 2 fire stairs, sometimes more. The stairs are enclosed in fire-resistant shafts, and they have doors that are self-closing and fire-rated. They provide a safe path for occupants to evacuate the building in an emergency. But here's the problem with fire stairs in a tall building. They're tall. If you're on the 50th floor and you have to walk down 50 flights of stairs, you're going to be exhausted by the time you reach the bottom. And if you're a firefighter trying to carry heavy equipment up to the 50th floor, you're going to be exhausted too. That's why modern tall buildings also have firefighter elevators. These are special elevators that are protected from fire and smoke and are designed to be used by firefighters during a fire. They have their own power supply and their own water supply, and they are located in a fire-resistant shaft. And then there's the smoke management system. In a fire, smoke can be just as deadly as the flames. Smoke can travel through the building's ventilation system, filling the floors above the fire with toxic fumes. To prevent this, tall buildings are equipped with smoke management systems that use fans and dampers to control the flow of smoke. The goal is to keep the smoke contained to the area of the fire and to keep the fire stairs and corridors clear of smoke. All of these systems are coordinated by a building management system, a computer network that monitors and controls the building's mechanical, electrical, and plumbing systems. The building management system can alert the building operator to problems, automatically adjust the HVAC settings, and even shut down equipment in an emergency. So, the next time you're in a tall building, take a moment to appreciate the invisible city around you. The pumps and pipes and ducts and wires that keep the building running. The fire alarms and sprinklers that keep you safe. The elevators that move you up and down. All of it hidden. All of it essential. But there's one more invisible system we haven't talked about yet. One that's so important that it's one of the main constraints on how tall we can build. It's time to talk about the elevators. There's a moment when a skyscraper transitions from a structural achievement to a practical building. It happens when the first elevator doors slide open. Because without elevators, a tall building is just a very tall staircase, and nobody wants to climb 40 flights of stairs. We touched on this earlier, but the elevator is so fundamental to the skyscraper that it deserves a closer look. The elevator is the vertical highway of the building. It moves people, supplies, and sometimes even entire vehicles from floor to floor. It's the circulatory system of the building, and without it, the building is essentially dead. But elevators are not simple. They're complex machines that have to balance speed, safety, efficiency, and comfort. And as buildings get taller, the elevator problem gets harder. Here's the issue. In a 50-story building, you can have a reasonable number of elevators that serve all floors. But as the building gets taller, you need more elevators to handle the increased traffic. And each elevator shaft takes up floor space on every floor it passes through. If you have too many shafts, you lose too much usable floor space. The building becomes uneconomical. This is called the elevator problem. It's one of the main constraints on how tall we can build, and solving it has required some of the most creative thinking in skyscraper engineering. The first solution was the sky lobby. This was introduced in the World Trade Center towers in the 1970s, but the concept had been around for decades. In a sky lobby system, the building is divided into zones. Express elevators run from the ground floor to a sky lobby at the top of each zone. From the sky lobby, local elevators serve the individual floors in that zone. This means that the express elevators only have to go to a few floors, which reduces the number of shafts needed. And the local elevators only serve a small number of floors, so they can be smaller and slower. The result is a more efficient use of space. The World Trade Center had sky lobbies on the 44th and 78th floors. Passengers would take an express elevator to one of these floors, then transfer to a local elevator to reach their final destination. It was an elegant solution that allowed the towers to rise to 110 stories. Today, almost every super-tall building uses some version of the sky lobby system. The Burj Khalifa has sky lobbies on several floors. The Shanghai Tower has them. The One World Trade Center has them. It's a standard feature of tall building design. But the sky lobby system has a downside. It requires passengers to transfer elevators, which can be inconvenient. If you're a visitor to a high floor, you have to take one elevator to the sky lobby, then another to your floor. It's a minor inconvenience, but it's noticeable. So engineers are always looking for better solutions. One promising idea is the destination dispatch system. In a destination dispatch system, you tell the elevator where you want to go before you get in. The system then assigns you to a specific elevator that will take you directly to your floor, possibly with a few stops along the way. This reduces the number of stops and makes the trip faster. Another innovation is the double-decker elevator. This is an elevator with two cabs, one above the other, that can stop at two floors at once. This is particularly useful in buildings with sky lobbies. A double-decker elevator can drop passengers off at two sky lobbies simultaneously, doubling the capacity of the express elevator system. And then there are the high-speed elevators. Modern elevators can travel at speeds of up to 40 miles per hour, or even faster. The Burj Khalifa has elevators that travel at about 45 feet per second, or about 31 miles per hour. At that speed, you can travel from the ground floor to the observation deck on the 124th floor in about a minute. But high speed comes with challenges. At high speeds, elevator cars create air pressure changes that can make passengers' ears pop. The cars have to be specially designed to reduce noise and vibration. The guide rails have to be perfectly straight and smooth. The cables have to be strong enough to handle the weight and the speed. And that brings us to the cables. Elevator cables are one of the most critical components of the elevator system. In a tall building, the cables have to be strong enough to support the weight of the car and its passengers. But they also have to be flexible enough to bend around pulleys. and they have to be durable enough to last for many years. Traditional elevator cables are made of steel wire rope. But steel rope has a limit. At some point, the rope becomes too heavy for its own weight. The weight of the rope itself becomes a significant load. For very tall buildings, engineers have started using carbon fiber cables. These are lighter and stronger than steel, and they can handle the height. But even with the best cables, the elevator problem remains. The taller the building, the more elevators you need. And the more elevators you need, the more floor space you lose to shafts. For now, the Sky Lobby system is the best solution we have, but engineers are working on new ideas. One idea is the ropeless elevator, which uses linear motors to move the elevator car without cables. This would eliminate the need for a machine room at the top of the building and could allow for multiple cars in a single shaft. It's a promising idea, but it's still in the early stages of development. The other challenge is evacuation. In an emergency such as a fire, people need to get out of the building quickly. Stairs are slow, elevators are fast. But elevators are usually shut down during a fire to prevent people from being trapped in a burning shaft. Some modern tall buildings are starting to include evacuation elevators. These are elevators that are designed to be used in an emergency. They have their own independent power supply, they're protected from fire and smoke, and they're operated by trained personnel. They can move people down to safety much faster than stairs. All of this requires careful planning and coordination. The elevators have to be integrated with the building's structural, mechanical, and electrical systems. They have to be placed in the right location. They have to be sized correctly, and they have to be maintained properly. So the next time you ride an elevator, think about what's happening behind the scenes. The cables, the pulleys, the motors, the control systems. Think about the years of engineering that went into making that ride smooth and safe. And think about all those people who have to be moved every day. It's a remarkable feat of engineering. But there's one more challenge that we haven't talked about yet. A challenge that is invisible but essential. We've conquered gravity. We've conquered the ground. We've even conquered the wind. But now we have to face something that comes from within. The people. We've talked about gravity. We've talked about the ground. We've talked about the weight of the building pressing down. But there's another force that a skyscraper has to contend with. One that's invisible, unpredictable, and at high altitudes, incredibly powerful. That force is wind. If you've ever stood at the top of a tall building on a windy day, you know what I'm talking about. You can feel the building move. It's a slow, gentle sway, like being on a ship at sea. That sway is the building's way of handling the wind. If the building were perfectly rigid, the wind would tear it apart. Instead, it bends, absorbing the energy of the wind and dissipating it through its structure. This is the dance with the wind. And it's one of the most important and fascinating aspects of skyscraper design. Let's start with the basics. Wind is air in motion. At ground level, the wind is slowed down by friction with the ground, by buildings, by trees. But as you go higher, the wind speeds up. At 300 feet, the wind can be 30 to 40% faster than at ground level. At 1,000 feet, it can be 50 to 60% faster. And that faster wind creates much larger forces on the building. The force of the wind on a building increases with the square of the wind speed. That means if the wind speed doubles, the force increases by a factor of 4. So a wind that's only a little stronger can have a dramatically larger effect. The wind also creates different types of forces. First, there's the direct pressure on the windward side. This is the force of the wind pushing against the building. Second, there's suction on the leeward side. As the wind flows around the building, it creates a low-pressure area on the downwind side. This suction pulls the building toward the wind. Third, there's the lateral force. Wind flowing around a building can create vortices, spinning pockets of air that pull the building from side to side. This is called vortex shedding. All of these forces have to be accounted for in the design of the building, and they have to be accounted for in a dynamic way, because the wind is always changing. Early skyscraper engineers dealt with wind in a relatively simple way. They made the buildings heavy and stiff. The Monadnock building with its 6-foot-thick brick walls was so heavy that the wind barely affected it. But that approach doesn't work for modern skyscrapers. They're too tall, too light, and too flexible. They need to be designed to move with the wind. The first step in designing for wind is understanding what the wind will do. That's where wind tunnel testing comes in. Engineers build a scale model of the building, usually at a scale of 1 to 200 or 1 to 500. They put the model in a wind tunnel and measure the forces acting on it. They test different wind speeds, different wind directions, and different wind profiles. But a wind tunnel model can't capture everything. It can't perfectly replicate the turbulence of the wind around nearby buildings. So engineers also use computer simulations. They create detailed digital models of the building and its surroundings, and they use computational fluid dynamics to simulate the wind flow. The results of these tests and simulations are used to design the building's structural system. The engineers might add extra bracing to certain floors. They might make the columns thicker on one side. They might add a tuned mass damper. We talked about tuned mass dampers earlier, but they're worth exploring in more detail. A tuned mass damper is a large mass, usually a block of steel or concrete, that's mounted near the top of the building. The mass is connected to the building by springs and dampers. When the wind pushes the building to the right, the mass lags behind, and the springs pull the mass to the right. This creates a force that opposes the building's motion, reducing the sway. The mass is tuned to the building's natural frequency. The building's natural frequency is the rate at which it would sway if you gave it a push and let it go. If the wind causes the building to sway at its natural frequency, the sway can build up dramatically. This is resonance. The tuned mass damper is designed to prevent resonance by adding damping to the system. The most famous tuned mass damper is probably the one in the Taipei 101 building in Taiwan. It's a massive steel sphere, 660 metric tons, suspended from cables near the top of the building. It's so large that it's a tourist attraction. You can go up and look at it. During a typhoon, the sphere can swing more than a meter, counteracting the building's motion. Other buildings use different types of dampers. Some use liquid dampers, tanks of water that slosh back and forth. Some use friction dampers, devices that use friction to dissipate energy. Some use active dampers, which use sensors and actuators to actively push the building in the opposite direction of the wind. But even with the best dampers, the building will still sway, and that sway can be uncomfortable for the occupants. Human beings are surprisingly sensitive to motion. We can feel accelerations as small as 1 or 2 feet per second squared. If the building sways too much, people can get motion sickness, so engineers also design for comfort. They set limits on how much the building can sway. The standard for office buildings is that the building should not sway more than a certain amount in a once-in-10 years wind. The limits are small, usually on the order of inches for the upper floors. Even a few inches of sway can be noticeable, so the engineers have to be very careful. The shape of the building can also affect the wind loads. A rectangular building with sharp corners creates strong vortices. A building with rounded corners, or a tapered shape, creates weaker vortices. The architects can use this knowledge to shape the building in ways that reduce wind loads. A classic example of this is the Burj Khalifa. Its stepped, tapered shape is designed to break up the wind flow. The wind flows around the building in a way that doesn't create strong vortices. The shape of the building is part of the structural system. And there's another aspect to the dance with the wind that's often overlooked. The wind doesn't just push on the building, it also creates a pressure difference between the windward and leeward sides. This pressure difference can create a force that pulls the building toward the wind, adding to the load. Engineers have to account for this as well. So the next time you're at the top of a tall building on a windy day and you feel the building sway, remember the dance. It's a carefully choreographed dance between the building and the wind, a dance that the building is designed to perform safely. The building is moving, but it's moving within a safe range. The sway is a sign that the building is working the way it's supposed to. It's absorbing the energy of the wind and dissipating it through the structure. But there's another force that's even more dramatic than the wind. It's a force that can shake the ground itself. It's the earthquake. The wind is a constant presence, a force that pushes and pulls at the building every day, every night, every season. But there's another force that's even more powerful, even more unpredictable, and potentially even more destructive. It's a force that comes from the ground itself. It's the earthquake. If you're building a skyscraper in California or Japan or Chile or any other seismically active region, you have to design for earthquakes. And that's a completely different challenge from designing for wind. Wind loads are predictable. You know the wind speeds, you know the frequencies, you can model them in a wind tunnel. Earthquakes are different. You don't know exactly when they'll happen, how strong they'll be, or how long they'll last. All you can do is design to survive the expected shaking and hope for the best. So how do you design a skyscraper to survive an earthquake? The answer is surprisingly counterintuitive. You don't make it rigid, you make it flexible. Here's why. An earthquake shakes the ground. The ground moves back and forth, up and down, in a complex pattern. If the building is rigidly attached to the ground, it has to move with the ground. If the ground moves a foot to the left, the building has to move a foot to the left. But the building is tall and heavy. Its inertia wants it to stay still. That creates a huge force on the building. If the force is too large, the building will break. But if the building is flexible, it can absorb the motion of the ground without breaking. Instead of fighting the shaking, it moves with it. The building bends and sways, but it doesn't break. This is called seismic isolation or base isolation. A base-isolated building sits on a system of bearings and dampers that separate the building from the ground. The bearings are usually made of rubber and steel. They allow the building to move laterally without transmitting the full force of the ground shaking to the structure above. The dampers absorb energy, reducing the motion. The building essentially floats on a cushion. This technology was developed in New Zealand in the 1960s and is now widely used in earthquake-prone regions. It's so effective that many hospitals, emergency response centers, and other critical facilities are base-isolated. But base isolation is expensive, and for a very tall building, it can be difficult to implement. The building is so tall that even with base isolation, the upper floors can still experience significant shaking. That's where active systems come in. Active seismic control systems use sensors and computers to detect the shaking and then apply forces to the building to counteract it. These systems can be very effective, but they're also complex, expensive, and require power. The most common approach for tall buildings is passive control. This means designing the building with enough flexibility and damping to survive the shaking. The building is designed to sway, and it's designed to sway safely. The key to this design is something called the seismic response factor. This is a measure of how much the building will amplify the ground shaking. A building with a high response factor will shake much more than the ground. A building with a low response factor will shake about as much as the ground, or even less. The response factor depends on the building's natural frequency. Every building has a natural frequency, a rate at which it would sway if you gave it a push and let it go. The higher the building, the lower the natural frequency. A short, stiff building has a high natural frequency. A tall, flexible building has a low natural frequency. The ground shaking during an earthquake also has a range of frequencies. If the ground shaking includes frequencies that match the building's natural frequency, the building will experience resonance. The swaying will build up dramatically. This is what happened to the Mexico City skyscrapers during the 1985 earthquake. The ground shaking had a frequency that matched the natural frequency of many of the buildings, and they collapsed. The solution is to design the building so that its natural frequency is different from the expected frequencies of the ground shaking. This is usually done by making the building more flexible, lowering its natural frequency. But there's another problem. The building's natural frequency changes during the earthquake. As the building shakes and deforms, its stiffness changes. The natural frequency drifts. This makes it hard to avoid resonance. So engineers use a combination of strategies. They use base isolation or seismic isolation. They use dampers. They design the building to be ductile, to be able to deform plastically without breaking. And they design the connections to be strong enough to handle the forces. The most important part of earthquake-resistant design is the connection between the beams and columns. In an earthquake, the building's beams and columns have to be able to move relative to each other without breaking. This is done by designing the connections to be strong in bending, but flexible in shear. Another key element is the shear wall. A shear wall is a wall that is designed to resist lateral forces. In a tall building, shear walls are often located at the core of the building, around the elevator shaft. They provide stiffness and strength to the building. The design of the shear walls is critical. They have to be strong enough to resist the forces, but they also have to be ductile enough to deform without breaking. Reinforced concrete is the most common material for shear walls. The steel reinforcement provides ductility, while the concrete provides compressive strength. And then there are the moment frames. Moment frames are frames with rigid connections that can resist bending. They're the heart of the seismic design of many tall buildings. In a moment frame, the beams and columns are connected so they form a continuous structure. The connections are designed to be strong enough to resist the forces of an earthquake. The end result of all this engineering is a building that can survive an earthquake. The building will shake, it will deform, it may even crack, but it won't collapse. The occupants will be safe. So the next time you're in a tall building and you feel the ground shake, remember the engineering that went into it. The base isolation, the dampers, the shear walls, the moment frames. It's a symphony of engineering designed to keep you safe. But before we can design a building for earthquakes, before we can design it for wind, we have to understand something even more fundamental. We have to understand the structural system itself. We've talked about the skeleton. We've talked about the skin. We've talked about the wind and the earthquakes, but there's one more aspect of skyscraper design that we haven't fully explored. It's the part that makes it all possible. It's the structural system itself. The structural system is the underlying logic of the building. It's how the building resists the forces of gravity, wind, and earthquakes. It's the arrangement of columns, beams, walls, and floors that holds everything together. And it's not just about strength, it's also about efficiency. A building that uses more steel than it needs is a building that costs more than it should. A building that uses less steel than it needs is a building that's unsafe. The challenge is to find the sweet spot, a structural system that's strong enough, stiff enough, and efficient enough to meet the demands of the building. The history of skyscraper structural systems is a story of continuous improvement. Each generation of engineers has found ways to build taller, with less material, using smarter designs. We've already talked about the earliest systems. The rigid frame was the first major system. It was a simple grid of columns and beams with rigid connections. It worked well for buildings up to about 40 stories, but as buildings got taller, the rigid frame became less efficient. The columns at the base had to be very large to resist the bending forces from the wind. The next major system was the braced frame. In a braced frame, diagonal members are added to the grid. The diagonal members create triangles, which are the most stable geometric shape. The triangles resist lateral loads, reducing the bending forces on the columns. This allowed for taller buildings with smaller columns. But the diagonal members have a downside. They take up space. They get in the way of windows and doors. For an office building, where open floor plans are desirable, braced frames can be a problem. Then came the tube frame. This was the system that revolutionized skyscraper design. The tube frame was developed by Fazlur Khan, a Bangladeshi-American engineer who worked for Skidmore, Owings and Merrill. Khan realized that by placing the columns close together around the perimeter of the building, he could create a hollow tube that was incredibly stiff and efficient. In a tube frame, the building acts like a giant box. The exterior columns are the walls of the box, and the floors are the dividers. When the wind pushes on the building, the force is transferred to the exterior columns. The columns act like a tube, distributing the load down to the foundation. This is much more efficient than a rigid frame because the material is used more effectively. The first building to use a tube frame was the John Hancock Center in Chicago, completed in 1969. The Hancock Center was 100 stories tall, and it used a modified tube frame called a trussed tube. The diagonal members on the facade were part of the structural system. They weren't just decoration. The next step in the evolution of the tube frame was the bundled tube. This was also developed by Khan. In a bundled tube, multiple tubes are bundled together, creating a larger tube. The Sears Tower, completed in 1973, was built with a bundled tube. The building is actually 9 tubes bundled together. The tubes are visible as the stepped profile of the building. The bundled tube is even more efficient than a single tube. The interior tubes provide additional stiffness, and the stepped profile reduces wind loads. The Sears Tower was the tallest building in the world for 25 years. Since the Sears Tower, other structural systems have been developed. The composite frame uses a combination of steel and concrete. The concrete provides strength and stiffness, while the steel provides ductility. The outrigger frame uses horizontal trusses at mechanical floors to connect the core to the perimeter columns. This provides lateral stability. And then there's the system used for the Burj Khalifa. It's called a buttressed core. The building has a central core that is reinforced with 3 wings, or buttresses. The buttresses provide stability and reduce the load on the core. It's a system that's perfectly suited for the desert environment of Dubai. All of these systems are the result of careful analysis and engineering. The engineers use computer models to simulate the behavior of the building under different loads. They test different configurations, different materials, different connection details, and they choose the system that best meets the needs of the building. The structural system is the foundation of the building. Without it, the building is just a pile of materials. But with it, the building becomes something more. It becomes a structure that can resist the forces of nature and stand for 100 years or more. And now we've reached the end of our journey. We've gone from the ground up. We've explored the history, the materials, the engineering, the design. We've seen how a skyscraper is built, from the foundation to the final touch. But there's one more chapter to write, a chapter about the future. We've traced the skyscraper from its humble beginnings in the masonry of ancient Rome, through the iron and steel of the Industrial Revolution, to the soaring glass towers of the modern era. We've seen how engineers learned to fight gravity, wind, and earthquakes. But the story is not over. The skyscraper is still evolving. Every year, buildings get taller, smarter, and more efficient. And the future holds even more possibilities. So what will the skyscrapers of tomorrow look like? How will they be built? How will they work? And what will it take to push even higher, beyond the mile-high mark? The first thing to understand is that the future is already being built. There are dozens of super tall buildings under construction right now around the world. In China, in the Middle East, in Southeast Asia, new records are being set. And each of these buildings is a testbed for new technologies and new materials. One of the most exciting developments is the use of high-strength materials. The steel and concrete we use today are much stronger than what was available even 20 years ago. High-strength concrete can have compressive strengths of over 15,000 pounds per square inch. That's more than 3 times the strength of the concrete used in the Empire State Building. High-strength steel can have yield strengths of over 100,000 pounds per square inch. These stronger materials allow engineers to build taller buildings with smaller columns and thinner walls. But even stronger materials have limits. To go beyond about a mile in height, we need new structural systems. One promising idea is the exoskeleton. In an exoskeleton, the structural system is on the outside of the building. The exterior walls are the structure, not just a skin. This is a return to the load-bearing wall concept, but with modern materials. The exoskeleton can be made of steel or concrete, or a combination of both. It can be designed to be very stiff, which is important for resisting wind and earthquakes. Another promising idea is the superframe. The superframe is a system that uses a small number of very large structural elements to carry the load. The elements are located at the corners of the building and at the core. The superframe is very efficient because it uses a minimal amount of material. And then there's the concept of the self-sustaining skyscraper. This is a building that generates its own power and recycles its own waste. Solar panels on the roof and on the exterior walls can generate electricity. Wind turbines can generate power from the wind. The building can collect rainwater and treat it for use. It can even have vertical farms that produce food for the occupants. This is not science fiction. There are already buildings that incorporate some of these features. One of the most famous sustainable skyscrapers is the Shanghai Tower in China. It's not the tallest building in the world, but it's one of the greenest. The building has a double-skin facade that provides natural ventilation. It has wind turbines that generate power for the building. It has rainwater collection systems, and it's designed to be energy efficient. The Shanghai Tower is also an example of another trend, the mixed-use building. Mixed-use buildings combine office, residential, retail, and hotel space in one structure. This creates a vibrant community that's active 24 hours a day. It reduces the need for commuting, which is good for the environment. And it creates a more interesting and diverse urban environment. But there's a challenge with mixed-use buildings. Different uses have different requirements. An office needs large, open floor plates. A residential building needs smaller, more intimate spaces. A hotel needs easy access and lots of services. Designing a single building that can accommodate all of these uses is a challenge. But it's a challenge that architects and engineers are increasingly willing to take on. Another trend is the vertical village. This is a building that's designed to be a community in itself. It has public spaces, green spaces, and community facilities. The building is not just a place to live and work, it's a place to gather and socialize. The future of skyscrapers is also being shaped by technology. Building Information Modeling, BIM, is a powerful tool that allows architects and engineers to create detailed digital models of buildings. The models can be used to simulate the building's performance, to detect conflicts, and to optimize the design. BIM is already widely used, but it's becoming more sophisticated all the time. Then there are the new materials. Carbon fiber composites are incredibly strong and light. They're already used in airplanes and race cars. Could they be used in skyscrapers? The challenge is cost. Carbon fiber is expensive compared to steel. But as the technology improves, the cost will likely come down. There's also the possibility of using 3D printing to build skyscrapers. 3D printing is already being used to build houses. Could it be used to build a skyscraper? The challenge is scale. Printing a building as tall as a skyscraper would require an enormous printer. But it's not impossible. There are companies working on this. And what about the elevators? We've talked about the elevator problem. To build even taller buildings, we need better elevators. That might mean ropeless elevators. That might mean elevators that can move horizontally as well as vertically. That might mean elevators that are powered by linear motors. All of these developments are happening right now. The skyscraper is not a finished concept. It's a work in progress, and it will continue to evolve as long as humans have the ambition and the ingenuity to build higher. So where does that leave us? We've come a long way. From the ancient Romans to the modern masters of engineering, we've seen how the skyscraper has shaped our cities and our lives. We've seen how it's a symbol of human ambition and achievement, and we've seen how it's a testament to the power of engineering. The next time you look up at a skyscraper, think about all of that. Think about the millions of hours of thought and labor that went into it. Think about the millions of tons of steel and concrete. Think about the wind and the earthquakes that it was designed to resist. And think about the people who will live and work in it. Then remember this. The skyscraper is not just a building. It's a story. A story about human ingenuity, human ambition, and human achievement. And that story is still being written. We've spent a long time talking about how skyscrapers work. We've explored the history, the engineering, the materials. But there's one question we haven't fully answered. A question that gets to the heart of why skyscrapers exist in the first place. The question is this: why do we build them? What's the point of going so high? The answer is not simple. It's a mix of economics, ego, and aspiration. But if you want to understand the skyscraper, you have to understand the economics. Because at the end of the day, a skyscraper is a machine for making money. And that machine has to be profitable. Let's start with the basics. The value of a piece of land is determined by its location. Land in the middle of Manhattan or downtown Chicago or the financial district of London is incredibly valuable. There's a lot of demand for space in these areas, and there's only so much land available. The only way to create more space is to build up. A skyscraper allows you to create a huge amount of rentable floor space on a small piece of land. The value of that floor space can be enormous, but it costs a lot to build a skyscraper. The cost of materials, labor, and engineering is enormous, and the cost increases with height. At some point, the cost of building higher exceeds the additional revenue you can generate from the extra floors. That's the point where it no longer makes economic sense to build taller. This is called the premium for height. It's the extra cost you pay for each additional floor. The taller the building, the higher the premium. The structure has to be stronger, the foundations deeper, the mechanical systems more complex. The building becomes less efficient. Each additional floor costs more than the one before. So developers have to do the math. They have to calculate the potential revenue from the building, subtract the construction costs, and see if the project makes sense. If the numbers don't work, the building doesn't get built. That's why the early skyscrapers were clustered in downtown areas. The land was valuable, and the economics made sense. The Empire State Building was built in Midtown Manhattan, one of the most expensive pieces of real estate in the world. It was built because the developers believed they could fill the building with tenants and make a profit. But sometimes the economics don't work. The Empire State Building opened during the Great Depression. The building was only 23% occupied. It lost money for years. It was nicknamed the Empty State Building. It took decades for the building to become profitable. There's also the ego factor. Many of the world's tallest buildings were built not because they made economic sense, but because someone wanted to make a statement. The Chrysler Building was built because Walter Chrysler wanted to have the tallest building in the world. The Sears Tower was built because Sears wanted to consolidate its corporate headquarters. The Burj Khalifa was built because Dubai wanted to put itself on the map. These buildings are not just office buildings, they're symbols, they're monuments, they're statements about the ambition and power of the people who built them. But even the ego-driven projects have to make some economic sense. The developers need to be able to fill the building with tenants. The Burj Khalifa may be a symbol, but it also has to generate revenue. It has office space, residential space, and a hotel. It's a mixed-use building designed to be profitable, so the economics are always there, even when the ego is driving the project. There's another factor that affects the economics of skyscrapers: the cost of financing. Building a skyscraper is expensive. The developer has to borrow hundreds of millions or even billions of dollars. The interest on that debt is a huge expense. If the project takes too long to complete, or if the building doesn't fill up quickly, the developer can lose a lot of money. That's why speed is so important. The faster you can build the building, the sooner you can start collecting rent. The Empire State Building was built in 14 months, an astonishingly fast pace. The developers knew that time was money. There's also the cost of maintenance. A skyscraper is expensive to maintain. The elevators, the HVAC systems, the windows, the facade, all of it requires regular maintenance, and the taller the building, the higher the maintenance costs. It's expensive to wash the windows of a 100-story building, so a skyscraper has to generate enough revenue to cover all these costs. The rent has to be high enough to justify the investment. That means the building has to be in a prime location. It has to attract high-paying tenants. It has to be a desirable place to work or live. That's why so many skyscrapers are located in the financial districts of major cities. The tenants are banks, law firms, and other high-paying businesses. They're willing to pay a premium to be in the center of the city. But the economics are changing. The rise of remote work is changing the demand for office space. Companies are realizing that they don't need as much office space as they used to. They can let their employees work from home. This could have a huge impact on the skyscraper market. If the demand for office space decreases, the economics of building new skyscrapers may no longer make sense. But there's still a demand for residential space in city centers. People want to live close to work, close to entertainment, close to the action. That's driving the growth of residential skyscrapers. These buildings are apartments and condominiums, not just offices. They're designed for people to live in, not just work in. So the skyscraper is evolving. It's adapting to the changing needs of society, and that adaptation will likely continue. At the end of the day, the skyscraper is a reflection of its time. It reflects the economic conditions, the technological capabilities, and the aspirations of the people who build it. It's a product of its environment, and as the environment changes, the skyscraper will change with it. The future of the skyscraper will be shaped by the forces that shaped its past: economics, technology, and human ambition. The skyscraper is not just a building, it's a testament to what we can achieve when we combine vision, ambition, and engineering. We've traveled a long way together. From the ancient Romans to the modern masters of engineering, from the 2-meter-thick walls of the Monadnock building to the gleaming glass and steel of the Burj Khalifa. We've seen how the skyscraper evolved from a simple idea into a complex, sophisticated, and awe-inspiring feat of engineering. And now, at the end of this journey, it's worth taking a moment to reflect on what we've learned. Not just about buildings, but about ourselves. Because the skyscraper is more than just a structure, it's a mirror. It reflects our ambition, our ingenuity, our desire to reach higher. The first thing we learned is that skyscrapers are not just about height, they're about how you achieve that height. The structural system, the materials, the engineering, all of it is designed to overcome the forces of nature. To fight gravity, wind, and earthquakes. To create a safe, comfortable, and efficient place for people to live and work. We learned that the foundation is the most important part of the building. Without a solid foundation, nothing else matters. The foundation has to be strong enough to carry the weight of the building and transfer it to the earth. It has to be designed for the specific conditions of the site, and it has to be built with care and precision. We learned that the steel frame is the skeleton of the building. It's the structure that holds everything together. The frame has to be strong, stiff, and ductile. It has to be able to withstand the forces of nature without breaking, and it has to be designed to be efficient and economical. We learned that the curtain wall is the skin of the building. It's the protective layer that keeps out the weather and lets in the light. The curtain wall has to be strong, lightweight, and weatherproof. It has to be able to accommodate the movement of the building, and it has to be beautiful. We learned about the mechanical, electrical, and plumbing systems that make the building habitable. The systems that provide water, power, heating, cooling, and communications. These invisible systems are the lifeblood of the building. Without them, the building is just a shell. We learned about the elevators, the vertical highways that move people from floor to floor. We learned about the challenges of moving people in a tall building, and about the solutions that engineers have developed. We learned about the wind, the invisible force that pushes and pulls at the building. We learned how engineers design buildings to resist wind, and how they use dampers and other systems to control the sway. We learned about earthquakes, the ground-shaking force that can destroy buildings in seconds. We learned how engineers design buildings to survive earthquakes, how they use base isolation, dampers, and ductile materials to protect the building and its occupants. And we learned about the economics, the reason why skyscrapers exist in the first place, the need to create valuable space in crowded cities, the cost of building high, and the revenue that can be generated. All of this adds up to one thing: the skyscraper is a triumph of engineering. It's a testament to human ingenuity and human ambition. It's a symbol of what we can achieve when we combine vision, knowledge, and determination. But there's one more thing we learned, something that's easy to forget. The skyscraper is not just a building, it's a community, a vertical community of thousands of people living and working in close proximity. A community that relies on the building's systems to function, a community that is shaped by the building's design. The skyscraper is a city within a city. It has its own infrastructure, its own economy, its own culture. It's a place where people come together to create, to innovate, and to thrive. And that's perhaps the most important lesson of all. The skyscraper is not just a structure, it's a place where people live, work, and dream, a place that shapes our lives and our cities. So the next time you look up at a skyscraper, remember that. Remember all the history, all the engineering, all the human effort that went into it. And then remember the people who are inside it, the people who make it a living, breathing, vibrant place. The skyscraper is a symbol of our civilization. It's a symbol of our ability to reach for the sky. And as long as we continue to reach, the skyscraper will continue to evolve. It will grow taller, more sophisticated, and more sustainable. It will reflect our changing needs and our changing values. But it will always be a symbol of our ambition, our desire to build something extraordinary, to leave our mark on the world. We've come to the end of our journey, but the journey is never really over. Every day, somewhere in the world, a new skyscraper is being planned, designed, and built. Every day, we're pushing the boundaries of what's possible. Every day, we're reaching higher. So when you settle in tonight, look out the window, look at the skyline, and know that you're looking at a story of human achievement, a story that's still being written. Rest well. We've come to the end of our journey, but before we close this chapter, I want you to take a moment, just one moment. Look around you. Wherever you are right now, there's a good chance you're inside a building. And that building, whatever it is a product of everything we've talked about. Every principle, every innovation, every hard-won lesson from a century and a half of building tall is present in the structure that's holding you up right now. It might be a small building. It might be a house. It might be an apartment. It doesn't matter. The same physics that holds up a 1,000-foot skyscraper holds up a single-story home. The same materials, the same principles, the same engineering. The only difference is scale. That's what makes the skyscraper story so powerful. It's not just about the tallest buildings, it's about all buildings. It's about how we learned to create shelter that's safe, comfortable, and durable. It's about how we transformed our cities and our lives. Think about what we've covered. We started with the ground, the foundation that holds everything up. We learned that the ground is not always our friend. Sometimes it's soft and wet. Sometimes it's full of water. Sometimes it's shifting and unstable. But we found ways to work with it. We found ways to reach down to solid rock, or to spread the weight over a large area, or to use friction piles that grip the soil. We learned to build on anything. Then we moved up. We learned about the steel frame, the skeleton that carries the load. We learned how steel is made, how it's shaped, how it's connected. We learned about the different structural systems, the rigid frame, the braced frame, the tube frame, the bundled tube. Each one a refinement of the last. Each one allowing us to build taller and more efficiently. We learned about the curtain wall, the skin that protects the building. We learned that the skin is not just a pretty face, it's a carefully engineered system that has to keep out the weather, manage the temperature, and look good doing it. We learned about glass and aluminum and silicon seals and low emissivity coatings. All of it working together to create a comfortable interior. We learned about the mechanical systems, the lungs and the circulatory system of the building, the pumps and pipes and ducts that bring water and power and air to every floor, the HVAC systems that keep us warm in winter and cool in summer, the fire protection systems that keep us safe. We learned about the elevators, the vertical highways that move us from floor to floor. We learned about the sky lobbies and the double-decker cars and the destination dispatch systems, all designed to make the journey as fast and comfortable as possible. We learned about the wind, the invisible force that pushes and pulls at the building. We learned how engineers design buildings to resist wind, how they use wind tunnels and computer models to predict the forces, how they use tuned mass dampers and aerodynamic shaping to control the sway. We learned about earthquakes, the ground-shaking force that can destroy buildings in seconds. We learned how engineers design buildings to survive earthquakes, how they use base isolation and ductile materials and moment frames to protect the building and its occupants. And we learned about the economics, the reason why we build tall in the first place, the premium for height, the balance between cost and revenue, the desire for prestige and profit. All of this adds up to a single story. A story about human ingenuity, about our ability to overcome the forces of nature, about our determination to create something better. And here's the thing. This story is not over. It's still being written. Every day, engineers and architects are pushing the boundaries. They're testing new materials, new systems, new ideas. They're finding ways to build taller, lighter, stronger, more sustainable. The next generation of skyscrapers will be even more remarkable than the ones we have today. They'll be smarter, more energy efficient, more comfortable. They'll be integrated with their surroundings. They'll be communities, not just buildings. There are already buildings that generate their own power. Buildings that collect rainwater. Buildings that have vertical gardens and green roofs. Buildings that are designed to be net zero, meaning they produce as much energy as they consume. These are not science fiction, they're real, and they're becoming more common every day. There are buildings that are designed to be dismantled and reused. Buildings that are designed to adapt to changing needs. Buildings that are designed to be part of the city, not separate from it. This is the future of the skyscraper. And it's a future that's already arriving. So the next time you walk into a tall building, don't take it for granted. Don't just ride the elevator and look at your phone. Look around. Notice the structure. Notice the materials. Think about all the engineering that went into making that building possible. Think about the people who designed it, the engineers who did the calculations, the architects who shaped the vision, the construction workers who built it with their hands, the project managers who kept everything on schedule, all of them working together to create something that didn't exist before. Think about what that building means. It's not just a place to work or live. It's a symbol of what we can achieve when we work together, a testament to human creativity and human ambition. And then think about yourself. You're part of that story. Every time you enter a building, you're participating in that legacy. You're trusting the engineering. You're benefiting from the innovation. You're part of the community that these buildings create. So rest easy tonight. Know that the building around you is strong. It's designed to withstand the forces of nature. It's designed to keep you safe. It's designed to be comfortable. It's designed to last. All of that engineering, all of that history, all of that human effort is holding you up right now. It's working quietly in the background, doing its job, keeping you safe and comfortable. And it will continue to do so for decades to come. That's the quiet triumph of the skyscraper. Not the height, not the glamour, not the records. The quiet, everyday, almost invisible work of keeping us safe. The work of creating a shelter that's worthy of our trust. So thank you for joining me on this journey. Thank you for taking the time to learn about the incredible story of the skyscraper. And the next time you look up at the skyline, remember all of this. Remember the history, the engineering, the human effort. Remember that you're standing on the shoulders of giants. Now it's time to rest. The building will hold you. The night is quiet. And the sky, for now, is within our reach.